All right. Let me introduce our speaker. SK ready? So SK is a successful tech entrepreneur. He built his previous question answering startup, and that was acquired. Now he's building a new startup focused on NLP and image processing. So I will let him start.
Thank you. Thank you, Jen. Thank you for coming, guys. I'm going to talk about summarization and abstraction today. My focus, of course, as you mentioned, I think in image processing and captioning, but that's going to be not the focus today presentation. In NLP, one of the concern, focus, research area for companies is, can we make the text more concise, more precise? Can we summarize the text? That's the focus. And I'm going to talk about some of the research being done on the summarization part of it. To give an example, let's say if you have a news story which is running into, let's say, 1,000 words, but if you want to give a title for it, which will be just, let's say, 5 or 10 words, or if you want to give a couple of bullets of the summary of the news item, or if you want to write a brief 1-paragraph summary of the news item, then there are NLP models available to make this long text into short. I'm going to talk about some of the approaches and maybe I think a couple of solutions on how to arrive at a real good summary. Before I get into the summarization part, I want to talk about some of the building blocks for NLP. If you are a novice in NLP or if you are decently aware of what's happening in the NLP world, I think some of these terms you need to be aware of. First, for example, word embeddings is a concept where people need to understand how to translate text into some sort of a vector, some sort of numbers, because computers actually can process numbers, not really text. In my previous company, which I sold, we were trying to do comparison and ranking of documents, and recently I shared in a different meetup my research results on how to teach computers to comprehend text. In other words, you can do question answering on the text. For any of these things to happen, you have to have the deep learning model to process the text, and that can be only done using numbers. So word embeddings is one of the most fundamental foundation block, and if you're not aware of it, there are a bunch of blogs available. You can go refer to that, but for today's presentation, word embeddings are the way of translating text into numbers, into vectors, large size vectors. And of course, you might have heard of RNNs, recurrent neural networks, or LSTMs. LSTM is a variation, long short-term memory is a variation of RNN. In text processing, whether it's translating from one language to the other language, or summarization, or question answering, you got to feed in the text in a sequence into the neural networks. If you use an RNN, one of the problems researchers have found is called exploding gradient or diminishing or vanishing gradients. In other words, if you have a long sentence or if you have multiple sentences, if you have a paragraph which you are trying to feed in, and then eventually you want to ask a question to the model, for example, Sally went to the kitchen, John went there too, it was early in the morning, the weather was bright, it was 70 degrees centigrade, Sally said a hi too. With our language models, we can say Sally said a hi to John. But the actual answer for that question was in the first 2 sentences, that is around 20-30 tokens before the question. Now, the model has to remember the context and the meaning of the entire input feed. And RNNs were failing in the process because the gradients were either vanishing or exploding. So long short-term memory cells were invented, where the primary purpose is to take in temporal data, in this case text, where you got to input word after word or sentence after sentence, and it can process and remember the details. So that's LSTMs. I'm going to talk about more LSTMs. Sequence to sequence is another concept that came up a couple of years ago, where you use LSTMs to feed in text in a sequence and then use maybe the same LSTM to to output a different set of text. Let me take an example of language translation. If you have a text in English and you want to translate it into French, for example, you take an LSTM and then you feed in the input text. Let me show you a picture. This is an LSTM where the input text is A, B, C, and there is something called end of sentence token. And the moment you introduce end of sentence token into the LSTM, the model knows that you have reached the end of feed, input feed, and then it starts outputting the text what you want it to. For example, if it's a translation, A, B, C, E, O, S is, let's say, in an English, and it starts outputting W, X, Y, Z, E, O, S. So that's the translated part of it. So that's a sequence to sequence, where you input a sequence and you get a sequence out. Now, this is different from, let's say, a regular feed-forward neural network or even convolutionalist neural networks where you're doing image processing. You input one image and it outputs maybe the caption of it. And when you introduce a new image or the next image, LSTM would not, or the model would not even know what was the previous model. Whereas in LSTM, it has to remember the previous context. So sequence to sequence was another concept built on top of LSTM to process text in a temporal fashion to address whether it's language translation or summarization or Q&A and all of that stuff. So let me go back to my other building blocks. Encoder-decoder. This was the, I think even though theoretical encoder-decoder models were proposed quite some time ago, the implementable encoder-decoders have become popular only in the last 3 or 4 years. For that matter, the entire NLP, I would say, has become really, really popular only from 2013. That's when word-to-vec was introduced or invented, where you can translate text into vectors more easily, which also can capture the semantic information of the text. That's when the whole NLP world exploded, and it's really progressing fast. Encoder-decoder model, even though was proposed theoretically earlier, but it has become more famous now. Let me explain an encoder-decoder framework. It is a further extension of sequence-to-sequence model, but in an encoder or a decoder model, you are using 2 different LSTMs. You feed in the input into one LSTM, which is called encoder, and you give some other input, I'll explain what it is, some other input to the decoder. As the name suggests, it decodes the text. Again, if it's a question answering or a language translation or summarization, all of these problems could be solved using encoder and decoder model. Let me explain, and none of the NLP papers, none of the NLP research is complete if you don't use, want me to move? If you don't use the mathematical equations. I know many of you guys in your schools and colleges, you would have did the equations, but you might have forgotten, but I need to explain that. The primary output of an LSTM, actually LSTM has 2 outputs. The primary output for our type of problems, like as I said, question answering or summarization, is the hidden state. That's one of the outputs of an LSTM. So hidden state of an LSTM, in this case encoder, is computed based on hidden state at timestamp t, is computed based on the current input. For example, if you have 10 tokens or 10 words in a sentence, and if you're talking about t is equal to 5, the 5th word going in. So input at timestamp t and the hidden state at timestamp t minus 1. The hidden state is a function of the previous hidden state and the current input. And there's f is a function which is a nonlinear function which actually does some magic transformation of data and gives a hidden state hidden state ht, and then you can keep on computing for every input feed. And at the end of the whole input, you create something called context vector C. And context vector is a function of all the hidden states the encoder went through. And another transformation happens on all the hidden codes, and you have a single context vector that the encoder emits. And this hidden vector, hidden context vector, would capture all the essence, all the meaning, all the words, all the combination of the words in the input. Which sometimes when I wake up in the middle of the night, if I forget that I'm an NLP guy, I would always wonder, how is it possible that it can capture so much of information? But believe it, it does. And I've asked this question to so many guys. One of the guys I met, if you have not heard of this gentleman's name, I think you should really go back and read something about this person. A guy called Richard Socher. I even told him, I met him the other day, and my life's first selfie was with him. I never even imagined I would do a selfie, but I actually did a selfie with him. This guy is a Stanford PhD graduate 5-6 years ago. He had a company, MetaMind. It was acquired by Salesforce. Now he's a chief scientist on Salesforce. A young guy, but extremely insightful in his papers and in his blogs on NLP. He talks about how the encoders and decoders work. But anyway, I could not contain my excitement when I met him. So I just want to tell you that guy. I forgot my age and ran to him. Can I take a selfie with John? I took a selfie with him. So the context vector does capture all the information what you have fed in. Of course, there are some limitations to the context vector, and the subsequent research has found that there are some pieces of information missing. I will talk about in my research, and also some of the papers published later on, talk about how some of the problems are being addressed. But predominantly, current day research is built on this primary building block called encoder-decoder, especially on language translation and summarization is on encoder-decoder. So you actually have an encoder. It can be a single LSTM. It could be multiple bidirectional LSTMs too. For example, one research paper says that when you feed a sentence or a paragraph word by word in the same sequence, and by the time you reach, let's say, the 50th token or the 50th word or the 100th word, the information about the first word or the second word or the third word is captured lesser and lesser and lesser. So one research says that, can we feed input in one direction and the opposite direction to two different LSTMs, and the hidden vectors that both the LSTMs output can be concatenated to create a new hidden vector which will have more information about all the input feed. That's a research. I don't want to talk about that a little more, but right now, for our discussion, we will just say the feed is given in a sequence from left to right in English language. So once you have the context vector, you feed that context vector into a decoder. The probability of, so you are actually outputting words, and y1, y2, y3 to yn are the sequence of words the decoder is emitting, in this case if it's a translation. So the probability of yt, given all the previous outputs and the context vector, can be expressed in a function which is dependent on the previous output, the current hidden state of the decoder, and the context vector from the encoder. I'll try to confuse you more and more with more equations, but please bear with me. Without equations, you just can't read any technical paper. So that's a encoder and decoder, which I'll talk about that. The entire summarization research currently is some variation of encoder and decoder. So let me go back again to my encoder and decoder. There was a concept introduced called attention. So let's say you have an input of, let's say, 100 words, and you're translating that into a different language. After you output the 4th or the 5th or the 10th word in the output, in the decoder, the model, which is depending completely on the context vector alone, so the outputs are on the previous outputs, and the context vector alone is dependent. Sometimes this context vector, which did not capture all the information effectively, NLP scientists introduced a model called attention. In other words, when you are outputting a specific output word yt at a time step t, instead of taking a static context vector, take a dynamic context vector where you go back again into the encoder and compute a context vector ci, which is dependent on, so for to output a word yt, you not only use the hidden context of the decoder LSTM, but you go back and constantly check the hidden states of all the various inputs at any specific time. And these are the weights you consider. So if for yt, on the fifth word in translating, if you feel this yt need to depend more on the first word, this weight becomes more and more close to 1, and all of these weights become more closer to 0, so that the model effectively decreases the impact of the other words and highlights the impact of this word onto the language. And so, in other words, the model is going back again and checking on the input once again. That's a attention model. Attention models are being used more commonly now, because it's just definitely better than taking a static hidden context or context vector, going back and constantly checking for the context vector based on every time step actually enhances the quality of the output. So attention has become a common thing now.
Does that impact latency in a big way, because now you're forcing it to recompute encode every transaction?
Yeah. This computation will not have so much of impact. Actually, the latency or the response time is a big concern for the whole of NLP, but this will not contribute for the attention part. Actually, in the context of the benefits it's giving, because the quality of outputs is better and better. Whereas if you talk about latency, that's another entirely different research area. If you have these heavy matrices, the weights matrices, how do you restrict that? How do you make it sparse? How do you make it multiplications and mathematical computations faster and faster? That's where the focus is of late, to decrease the latency. But this won't has an impact as much.
So just one question. So why is the dynamic context, suddenly more valuable? Why the static context was not already useful?
Yeah. So I'll give an example. Let's say here the input is ABC. Let's say I'm just showing only 3. Let's say I have 1,000 inputs, and I'm doing a language translation, and from English to French. And French is not necessarily the same. It doesn't go from left to right in terms of interpreting the words. Sometimes, I don't know French, so I can't give any live example, but for a word that's coming at the start of a French sentence, maybe actually a word that appeared in the middle of an English sentence. Now, if this sequence is a long sequence, the weights, the context vector, which is actually a bunch of numbers, which is actually it's a vector weights, it's trying to capture the information about word 1, word 2, word 3, word 4, the dependency between word 1 and 2. It's capturing the entire semantic and the syntactic information. But the longer you go away, anything more than time steps 7 or 10 behind or ago, it doesn't capture that effectively.
On the other hand,
7 to 10 is...
that we only hold 7 words in memory.
7 is a research. What the research says, 7 to 10 is what people are showing. But let's say if you have 10 GPUs and if you're able to actually have a high processor thing, maybe I think it may capture more information, because then if you have a bigger vector, it can capture more information. But then people, I think, need to figure out how much of memory space do I have, how complicated the model can be. That's another issue too. So within the limitations, just to give a research example, the longest time a model took, which is an NLP plus convolutional, which is actually image processing, using around 15 GPUs. There's a model with 101 layers by Microsoft where they were trying to process images. It took 3 weeks for the model to train. They actually had 20,000, 30,000 images, so it takes 3 weeks with around 12 to 14 GPUs. GPU is extremely quick processing stuff, and it takes so much time. So if the infrastructure expands, maybe you will be able to do this more effectively, but with the current infrastructure, what is easily available to the researchers and corporations, 7 to 10 is the number people are throwing in. You can do maybe 20, 30, 50, 100. Ali, you have a comment? Gradients, yeah. Sure, I'm actually, so instead of RNNs, LSTMs are better. Instead of plain vanilla LSTMs, use with attention, it's better. Instead of just plain vanilla LSTM with attention, try to use, I'll talk about, I don't want to give away right now, there are intra-attention models, intra-neural attention models, where you can go back and reread one more time, not just from the encoder, but also on the decoder. There's another model where it's something called search. I'll talk about search, beam search and stuff, but as the research happens, researchers are finding better and better way of capturing information. 2 years ago, 3 years ago, it was LSTMs were the best. Then I think a couple of years ago it was LSTM with attention. But in the last 1 year, 2016 and 2017 papers are talking about attention, beam search, LSTMs of course, and then they're talking about multiple GPUs, and also the frameworks available. 2 years ago, TensorFlow was not that mature. I think now it's mature. I think 6 months ago, it was 1.0 was released, and you have Cafe2 or PyTorch. These are coming only off late. I think it's more effective now to rerun those models. Maybe they can try again, but yeah, it's taking more and more time. Let me see. Yes, next is beam search. Let me give an example of what it is, and then I'll try to connect all of these things together. So let's say there's an encoder here, and now you came to a decoder. You're inputting, you got the input, and of course you introduce a 0 vector, and now you're outputting the first word in language translation, or let's say in summarization, the first word is Y1, right? This is during training. So the model is predicting what should be the first word. Now, when it predicts, it actually has a probability. So it's a bunch of words from the vocabulary. You actually have to give a vocabulary to the decoder, and it predicts the probability of all the words that may be the first word. So the word which has high probability of 0.9, 0.993227, that in the vocabulary seems to be the first expected word. Right? That's what the model is predicting. But in the training, what you normally do is, to make it more effective, you introduce the same output back into the LSTM so that it knows my previous prediction is this, and my context vector from the encoder is this. So based on this, what should be my next word? So it's becoming more intelligent. But the problem is, Y1 is a predicted word. Probability of 0.9, 0.8, whatever is the number. In training, what people do is, to make it really intelligent model, they introduce the ground truth. When I say ground truth, let me take an example of language translation. Because I'm talking about summarization, let me take a different example. If you have a 10-word sentence in English, and you have, let's say, a 6-word output in French, you know what the translation is. You give the input in English, and you let the decoder model predict the first word in French. If it's wrong, you still know what the right word is, because the ground truth, you know. So you introduce a ground truth, but not the predicted word. And hence the potential errors the model is making in predictions is being eliminated, because you're giving the right answer at every step, even though it's making an error. or the error is 0.0001, but still that's an error, and you're eliminating the error by giving the ground truth. That's in the training model. But in testing, you don't have any ground truth because you're actually asking the model, tell me what the right word should be. What is the first word y1 should be? In such cases, the first word, let's say probability of P1, but the second word and the third word, the joint probability of your sequence also has to be high. Let's say the first word, for some reason, it says west. Oh no, the first word is bank. The second word can be off the river or bank on the street, because it could be referring to bank as a river or bank as a financial institution. The joint sequence of y1, y2, y3 also has to be collectively high to have your translation or to your summarization effective. So researchers, what they're doing is, instead of, once they predict the first word, they won't just ignore the first and just go to the second word. They say, after you make the prediction of the second word, can I still check whether the y1 and y2 as a sequence still has a high probability? And then if you go to the third word, so y1, y2, y3 as a joint probability still has to be high. So if you don't do such back check, and if you say y1 is my first high probability, I'm done with the y1, I'm going to make a y2 prediction, that's called maximum likelihood, and that's called greedy search. You are just done with the first best result you got, and you're done with it, and you're going for the second one. And if you compare to greedy search, if it's a full search, every time you have next output yn, you go back and check from y1 to yn, check one more time, is this the joint probability is the highest? And that's extremely costly. It's computing expensive. And people don't use full search too, and they've identified something called intermediary step, like a beam search. Instead of picking all the searches, you pick top k sequences. So if its k is 4, you check, let's say 3, a trigram all the time, and check the trigram has still the highest probability of the output. You had a comment?
So what is it that you're trying to maximize the probability of n-gram overall? Is like, because it sounds like a backtracking algorithm essentially.
The overall objective of the model is to have an output which has the highest probability to be accurate. So if it's a language translation, when you output the sentence translation, it has to have the maximum accuracy. Initially, researchers used to only pick for a greedy search where you have the first word, then based on the first word, you put it back again, the first word into the LSTM, it predicts a second word. If there is a minor error in the first word, that error propagates to the second word, maybe the error goes up a little bit, and the error goes to the third word, the error goes up. Eventually, the sentence may not be the most accurate sentence, even though it's still tolerable. But to increase the accuracy, there's a model where instead of having a greedy search, and to go for the full search, it will become costly to compute, they're identifying beam search, where you just identify top 5 sequences, top k sequences. That's whatever is n-gram. And you identify that n-gram, and then you go constantly check whether you have the highest probability of n-gram 2 to be satisfied with the output. So if you have a 50-word input feed in English, and you're doing a translation, which may be 20 or 30 or 40, you can't do, at the end of the 20th word, you can't go back from y1, that is first word, to the 20th word, do a joint probability and still look for it, because it's very, very costly to do it. So of every 3 gram, y1, y2, y3, y2, y3, y4, y3, y4, y5, so the n-gram, it constantly checks whether it still has the high probability.
But those sequences can have overlaps, and then your complexity explodes.
The sequences, sorry?
The sequences of 3 grams.
Hmm?
Right? How many 3 grams in say 3 numbers?
So
Say in 4.
you're right. It is more than greedy search, but definitely less than full search. And the reason is, let's say there are 5 outputs, 10 outputs, y1 to y10. If in a greedy search, after y1, you just check for y1 being the highest probability, go to y2, highest probability, y3, that's done. For full search, you do y1, check whether it's highest probability, do y2, check individually y2 is highest probability, and y1 and y2 as highest probability. Go to y3, y3 should be individually highest probable, then y1, y2, y3 as a n-gram should be highest. That's a full search, and it takes really complicated. So try to balance between the costly compute versus accuracy. Researchers have settled down on beam search, where they pick top k, top n-gram, let's say n number. So y1 should be of high probability, y2, y3 individually, and then y1, y2, y3. Then go to y4, then y2, y3, y4, you only check for those 3 to be the highest probable. And when you have y5 output, y3, y4, y5, you check the probability of only those 3 words being highest probable.
So we do take care of overlaps.
Yes, there is some overlap. Yeah, there's a compute. The compute expense will be definitely higher in a greedy compared to a greedy search, but the accuracy goes up too. So that's the beam search to enhance the accuracy of your outputs. So now let's see. I'll touch upon the LSTM. If people are not aware of what it is, or I can directly jump into the paper, the research, the real research. How many of you guys are you clear up with LSTM? What LSTM stands for? Okay, let me explain. You have the single feed-forward neural networks, which actually takes an input, gives an output. For example, if you want to predict in a regression model, if you want to predict what should be the value of a house based on the size and the number of bedrooms and the location and stuff, it takes one particular data set, 4 or 5 or 10 input items, compute, and then gives an answer for you. And that's one feed-forward neural network. When you give the second set data set for a different house, it wouldn't know anything about the previous house. It doesn't remember anything. In LSTMs, where you want to remember the temporal aspect, you want to remember what happened previously, what happened. You want the model to remember the past. So instead of neural network, feed-forward neural network is just one single layer, there are 4 layers of transactions happening in one LSTM cell. So it's like, imagine like it's just one magic box. It takes 2 inputs, gives out 2 inputs, but what it's doing in it is, in the process of, I'll explain what the transactions are inside, but what it's doing is, it is not only computing the output of that particular time step based on the current input, it also remembers what has been given input. So it has some sort of a memory. It remembers what's happening. So let's say you introduce Sally went to the mall. So you get Sally, and the next sentence she. So you know the gender of Sally now. So the LSTM model remembers that the object of discussion, Sally, is of a female gender. Until you talk about, let's say, John. Let's say she said hi to John. John wanted to go to play soccer. He checked the weather. The moment it is he, now you're talking about John with a different gender. So that it remembers. That's one aspect. It remembers so many other information too. Let's say Sally went to the kitchen. It remembers Sally was in the kitchen. So this memory aspect, or the cell actually has memory. So how does it do? So it has something called 3 different gates, or even though you call them as gates, but what it's doing is that it takes the 2 inputs and does different types of manipulation on the data, and at the end, so it takes the previous cell state and the new input, gives out the hidden state and the memory, cell memory. So in other words, what it's doing is it gives out 2 inputs, which the most important input is the memory, which actually is shown in picture here. this memory which is coming from the previous cell, it gets transformed based on the input using multiple mathematical equations. So effectively, in LSTM, it remembers the past. It actually has memory in LSTMs. That's a spectacular invention that happened, even though the model was introduced, I think, maybe a decade ago, but it has been really explained, implemented, and people are using it effectively only off late for the last 3 or 4 years, I would say. That's LSTM. These are some of the approaches used in summarization historically. The earliest summarization was just input a sequence into LSTM and let the LSTM predict what the outcome is based on the input LSTM. It's the same LSTM as I mentioned to you earlier. There's only one LSTM used initially for input and output, and the input to just before the translation starts, just before the summarization starts, the model is looking for a special token, special input, in this case end of sentence token, and the moment you introduce that, it knows that, okay, now my job to summarize, my job to translation starts, and it starts outputting. And every output it has after that, you put it back into the model, and it becomes a little more intelligent on what should be the next word based on the previous word it is predicted. So that's a sequence-to-sequence model which was used long time ago, where people have used only one LSTM, and later on people have used 2 LSTMs, where you have bidirectional LSTMs. Let me show a picture again. You have an LSTM where information is going from left to right. You stack it with another LSTM on top where you feed C, B, A, so in the reverse sequence, and at every time step. So at this time step, the model is taking A and the stacked model is taking C in it. And in this case, it's taking B and the other one is also taking B. And here, it's taking C and the stacked model is taking A. And both these two inputs are considered by the individual LSTMs, and it has each of the LSTM will emit its own hidden state, and those two hidden states are concatenated, which will have more effective information about the first word and the last word, or the one word at T, and the other word is T minus N, or N minus T. So that's the sequence-to-sequence model, but used in bidirectional. Refeed decoder is a model which was introduced by Richard Socher. Let me explain that. These are the papers and I'm going to talk about. This is the latest paper published by Richard Socher, where they've used effectively a decoder, an encoder and a decoder, but they have used 2 additional best practices which has increased the ROGUE score. ROGUE is, I forgot the expansion of ROGUE. It is this industry standard to compare summarizations. Now let's talk about summarization for a minute before we get into the model. Let's say you have a 1,000 word or a 10,000 word story. Now, if you ask me to summarize, I will do it in one way, and if I ask each one of you, your summarization is going to be very different. They may be different words. The way you write will be different. They all look different, but at the end of the day, they're all valid summary statements. One of the fundamental problems in summarization, so if you use this approach to build a solution for your company, and you want to say, okay, I'm a product company, I'm a Google, I'm Cisco, I'm NVIDIA, I have so much of documentation in the company, I want to create summaries for all of these documents, or I actually have announcements, public announcements, I had so many of these, I want my employees to read, so let me make a summary out of it. When you're trying to create summaries of this information, everyone writes differently. And to create a model, you got to have the full text and you got to have summaries too. Now, creating data sets out of the regular text and summaries is a very, very difficult task, because you don't have data sets available. So in that context, when people are trying to do research on how to create an effective summary, sometimes this rogue score which is used to compare how good the summary is, people have found the summary the model creates, even though has a very high rogue score, but just did not make any sense. Rogue score is comparison of a ground truth summary to a model generated summary where they pick n-gram phrases and then compare how many such n-gram phrases exist in the ground truth versus the model created summary. So sometimes you may find n-gram summaries, they may be positioned in such a completely wrong place that you don't make any sense, but still the rogue score of a model is really high. So in this model, for the first time, research sought to introduce a new technique. And so if you guys are going to go back and then do summarization, you may want to, this is a very, very nice idea. So the two ideas they have introduced, one is when you read a story and you want to summarize, you normally don't read the text in only once and start doing summary. You normally go back halfway through your summary, you go back and read it again, or at least you read a couple of times, 2 or 3 or 4 times, then you can do a good summary. So in this model, and the other paper also I'm going to talk about, researchers are talking about read and reread the model. And in the research searchers model, when they train the model on the complete story and the summary, they do a word by word comparison, but that's called maximum likelihood model comparison, where you want to make sure that each word in your summary is comparable to each word in the ground truth summary versus the model generated summary. But also they want to compare the entire summary is also comparable. So instead of inputting word by word, they input the entire summary. And because you can't put the entire summary in an effective matrix, they use a technique called reinforced learning. If you're not aware of the term reinforced learning, I'll explain in a context of teaching computers how to play games. Let's say you pick a game of chess. I know already computers, there are a lot of models available, not deep models available, but they're just basic logical models available to play chess, but let's ignore that we don't have those models. Let's assume that we don't have the models. And you're teaching the model to play the correct way of playing chess. Let's say you move one step and the opponent moves another step. The first step may be the correct one, second step may be the correct one, third step may be the wrong one, so-called wrong one, but the fourth, fifth, sixth, seventh, after the 8th step, maybe you win the game. So in other words, if you compare every step, whether that's the right step or not, you may not know whether you're going to win the game or not. So in the reinforced learning, every move the player moves is fed into the computer, and at the end of the last step, you tell the computer if all of these moves, whether it results in a winning game or a losing game. So if it's a winning game, you give a reward to the model, and if it's a losing game, you actually penalize the model. That's the only way of teaching a model to play a game, because sometimes you make a few correct steps, but still you end up losing the game, and you want to teach the computer how to play the correct game. Similarly, in summarization, they're using 2 different techniques. The maximum likelihood, that is, word by word they check whether the ground truth versus the model generated summary is correct, and they also introduce the entire the summary as a model. So let me explain. So here, this is a regular encoder where it inputs the output. They input the text, and the output is like a decoder. And if you put it together, this is how it looks. They input and the encoder and the decoder, and they have used encoder as a bidirectional encoder, and whereas a decoder is just a unidirectional. And they've used the concept of reinforced learning and the teacher-forced learning. Teacher-forced learning, as I mentioned to you, is a word-by-word comparison. When you have the ground truth of the summary and the model-generated summary, you compare word by word to see what is the maximum likelihood of that model-generated summary being accurate or comparable to the ground truth, and also introduce the entire summary as an input and check that against the model-generated summary. So that's the and this is the simpler explanation in a picture. Model generates a summary, and that is compared with the scorer, in this case the ground truth. And in any neural network deep model, every time you train a model, you ask the model to make a guess, and because you know the correct answer, you compare the two and then find out how much is the loss or a penalty, or how far away are you from the truth. So you identify the reward or penalty, you update the model, and then it keeps on going. This is a reinforced model. So remember I talked about the context vector from the encoder in a not even an attention model. It's a pure model. You have a static context vector, and when you use an attention model, you use the context vector at step I on the encoder. Whereas in this model, so that's the context vector at time step t for encoder is a sum of products of certain weights and hidden state at timestamp I for encoder. So that's the context vector from the encoder, and they also use the context vector for the decoder at timestamp t, which is a summation of certain weights and the hidden states of the decoder. So this is the newer invention. So till now, in an encoder and a decoder model with attention, the dynamic state of hidden states from the encoder only was being considered. Now, to enhance the accuracy of summarization, the dynamic hidden state of the encoder plus the dynamic hidden states of the decoder at any timestamp t is being considered for more an effective comparison of your summary being generated by the model compared to the ground truth. And they have, according to the results, what they are saying is the rogue score went up by 5 points. I don't understand the whole rogue score, how it works, but I think it's come to 45 points. 100, I think, is exactly the ground truth. Ground truth gets 100. I think the models is getting 45, which is better than a lot of other computer generated models. That's the. So let me explain. So there's the same thing again. You have the encoder. It's a bidirectional encoder. So you have the text going in. So in forward moving encoder, it's getting the word the, and the reverse directing encoder, it's getting the word, whatever is the last word, let's say tech. And combining these two words, it's creating a hidden state. And all hidden states of the encoder are being considered to create a context vector C, and there is an additional context vector created based on the outputs of the decoder till timestamp t, that is till now. So the context vector of the encoder and the context vector of the decoder and the hidden state of the decoder at timestamp t. All three vectors are being considered to identify the next word, the probability of the next word, whether it is expanded or became or increased, whatever it is, and the numbers right next to this are the probabilities of what should go next to it. That's the, actually sounds very common sense idea, but it's people I think I've not thought about earlier, I guess, but I think they're just trying to make it more and more complicated, but whatever it is, I think it seems to be not so computationally expensive, but accuracy was higher. That's what Richard Socher has done. Even though I did not mention this paper in my intro, there's one more which I think I mentioned to you earlier too. In addition to the encoder-decoder model approach being used, plus attention, plus beam search, plus the context vector from the encoder and a context vector from the decoder, plus using the maximum likelihood where you compare word by word from the summary, plus compare the entire summary as one entity. All of these best practices. Another practice by a different paper, I mentioned the paper at the bottom. I think we're going to have these slides available to the audience later on. Here, the newer suggestion is you feed the input not once, but you feed the input twice. So let me explain the model a little more. So I know this looks simple, but so this is the first LSTM, or the first encoder, and you have a second encoder, right? You input the first input token x1, x2, x3, and you have the hidden state initial. Typically a hidden state initial is all zeros, but then you have next hidden states computed based on the inputs. So you have the h11 is the first hidden state of the first LSTM, second hidden state of the first LSTM. So the hidden states are being computed, and for the second LSTM, so you input the same feed, but you not only give just the input, but also input the hidden state at that particular time and the final hidden state of the LSTM. So these three inputs, plus of course the initial hidden state of LSTM2, are being considered to create a new hidden state called H1 of 2, that is second LSTM, the first hidden state, and then you compute that. So if you want, I can explain again. So you have the first input, second input, third input for the LSTM1, and each time step, the LSTM will have its own hidden states. And for the second LSTM, you refeed. So it's rereading the same text again, but it's also taking the hidden states at every time step of the encoder 1, but also it's taking the hidden state of the final hidden state of the encoder are fed into every time step, and it's outputting. And the final hidden state, the second encoder outputs, is the one that is going to be used for creating summaries. So now it has read the same input twice. It has considered the hidden states of its own, that is the encoder 2, but it also has taken the hidden states of encoder 1. So it's reading the same text multiple times, and apparently the success rate, I think, has gone up. So let me actually see if I...
Before you jump from this slide, you train both of them simultaneously. It's not you finish the first one and then you introduce the second LSTM. You train them simultaneously.
Yes or no? Actually, you do both, because you got to train this model completely first. Otherwise, you would not be able to input this hidden state at the first step. So you actually do train the model first. Let me explain it again. Train this model completely first. Store the hidden states of encoder 1, and when you're training the next model, you pick up the first hidden state and the final hidden state. This is just for one sentence, and if you do two sentences, you actually becomes a little more complicated. So you actually introduce the hidden state of every time step, the hidden state at the end of the sentence, and then hidden state of the global, that is after the end of all sentences together. But this is for multiple sentences, so this is just the same application of this for multiple sentences, so we'll not talk about this. But you train the model completely, you have both Hn of 1 and H1 of 1, or H2 of 1, all of these, and then you introduce that into the model. So let me go back and check the equations. So at the end of the encoding process, you have the hidden state at timestamp 2 of the second encoder is dependent on the input at timestamp I, the hidden state from the first encoder at timestamp I, the final hidden state from encoder 1, and the hidden state from I minus 1 of encoder 2. All of these factors, so you do a little bit of a nonlinear activation on these data, and you get the hidden state, the final hidden state of encoder. And from there you compute the context vector at timestamp t, which is a summation of certain weights, and the hidden vector at hidden state at each timestamp of encoder 2. 1, 2, encoder, all this stuff. Anyway. And once you have that, you go to the decoder and you create the hidden state. In this case is represented as S. Hidden states, they were shown as H. The hidden state of decoder at timestamp t is dependent on the previous output, that is at output of the decoder at t minus 1, the context vector, and the hidden state of the context vector from encoder, and the hidden state t minus 1 of decoder. And then using the hidden state at timestamp t of decoder 2, you compute an output using an attention mechanism of previous hidden state and the output of the encoder. And here the funny thing is, in this model, what they said is, see, in a summarization model, the decoder has to have access to certain vocabulary. Now, the larger the vocabulary you provide to the model, the more rich the summarization is. Sometimes the words it creates in summary may not even exist in the original text, right? And that makes sense, because when you're summarizing, you may pick a different word but still communicate the same message. But to decrease the compute time, they have introduced the model of copying too. So you have a limited vocabulary so that your dimensionality of your vectors will be smaller. But let's say the model wants to predict a word which is not in the vocabulary because you are given a limited vocabulary. They have identified a unique, it's called OOV, out of vocabulary word. So you actually initiate a new embedding for the OOVs, and whenever an OOV vector is triggered, it goes and checks for a y minus t, that is the previous word. So it's looking to predict yt, but it's not in the vocabulary. What should I do? Go check with my y minus t what the word is, and that is the context around which my next word yt is going to be. Let me explain it again if you're not very sure. So you're predicting yt. If it's in the vocabulary, it just goes and gives the probability. If it's not in the vocabulary, it goes to yt minus 1, identify what the word is, because that was in the input sequence, goes into the input sequence to identify which word is comparable, and that's you compute that using this equation. And if it's not in this input sequence, it's not in the vocabulary, it inputs an unk into the summary. So sometimes they have found unks in it, but this model and the previous model, they have identified one of the problems of summarizations of late is repetition of phrases. Because the model is creating words, sometimes it may repeat the same phrase, a 2-word or a 3-word phrase, sometimes 4-word phrase too. To avoid repetitions, they found a very simple technique. They look for a trigram phrase. If the same trigram phrase exists in the input, they just cancel it, and the model it picks the model which is the next probable phrase or next probable word. So yt plus 1, yt plus 2, if that phrase is existing in the input, the yt plus 2, you take the yt plus 2 and go for the next word predicted in that time step to put it there as yt plus 2. That's pretty much from my side, and Sorry, I took a 5 minutes extra.
Let's thank the speaker. We have time for a few questions.
Yes, sir.
What an excellent presentation. Thank you. There's one thing that I was surprised that I did not hear, which is significance or something similar to that. When I think of good summarizations, one of the important things that a editor does in summarizations is identify what's really significant and speak to that and let pass the less important stuff. I'm surprised that I didn't recognize something like that. Have I missed something? Is there something in the works that does that?
In the summarization research, everyone is comparing to one single metric, and that's called rogue vector metric. That is spelled ROGUE. Yeah, this metric is what, and this is the industry standard term. I'm forgetting its gisting evaluation is the last two alphabets, and I'm forgetting what the first. But that's the metric they're using, and I'm not a linguist, so unfortunately I don't know how else to measure how excellent the summary is. Yes, sir.
I may have missed it because it has been a lot. Thank you very much. Very good presentation. But how in this main paper are they making sure they don't use repeated sentences in the summarization? Is by the reward, the group of metric, like getting the best one, or are they doing something specific for avoiding repeated sentences?
As I mentioned to you, they're constantly measuring a 3-phrase, let's say trigram. If the trigram in the model summary, if it's predicting the same as in the input, they would cancel. So let's say there are 3 words, yt plus 1, yt plus 2. The moment you predict yt plus 2, you check what was the 2 previous words, and combining these 3 words as a phrase exists in the input, they will go for the yt plus 2, whatever is the top probability, they cancel that and go for the next probable word. Yes, sir.
Last year I attended a conference of research social, and there he introduced GRUs. Can you tell something about that?
GRUs, gated recurrent units, are very, very similar to LSTMs. Actually, they are so similar. In LSTM, there are 3 gates, input, output, and forget gates. In GRUs, there are only 2 gates. And other than that, they're very, very similar. So what I've seen is in both the papers, they have implemented the model on both LSTMs and GRUs, and the results are very, very similar. Yeah, so it's a LSTMs and GRUs are variations of RNNs. Let's go with those fundamental things.
Thank you, sir.
Yeah, again, thank you.
Thank
Really
you.
helps to understand. Where are we in the state of the art? I know there's in imaging, we can have the best, imaging can be the best cancer cell recognition. Are we ready for real world applications, or do we still want to fall back to humans for this work?
We do have the state-of-art solution. I don't think we have any Wi-Fi. Do we have a Wi-Fi here? Huh?
Wi-Fi code is there.
The Salesforce recently announced a new progress in the summarization, which is actually Richard Soch's, and there's a article published in Forbes.com magazine. There on the website, you can actually see the model. It picks a text and it's printing the summary, and while printing each word in the summary, it's actually highlighting the 2 or 3 or 4 words it's focusing right now and creating a summary. It's a beautiful visualization of summary in action. I tried to copy put it into my PowerPoint. It doesn't work. It has to be a browser. I could not do it, but it's a very, very cool. It looks like you have the text and the overall text, and you have the summary, and the one by one the word is appearing in the summary, and whenever the new word appears, it shows in a different color, and the same color appears in the top or the middle or the end of the overall text. It's a beautiful visualization. So this guy, when I said he's like a god in NLP, I think he may be.
One follow-up. Some people just ramble all over the place, and you couldn't summarize them, no matter does the tool ever reject the article?
It goes back to, again, the definition of the rogue score, and I think it does that. What it does is, in rogue scores, there are rogue 1, rogue 3, and rogue L scores, where it takes 1 gram, 3 grams, and unlimited grams to check how many, in the ground truth and the model generated model, how many phrases are comparable, and it actually does a scoring. So based on the rogue score, I think it seems to be coming closer and closer to the human, but I don't think you can reach the human, because as I said, summary is one such aspect of NLP that every person can summarize differently. Whereas if it's a language translation, there's only one translation, almost one translation, let's say, from English to French. You can do it differently, maybe, I guess, but yeah. But summarization is so different. That's why I'm amazed at the progress these guys are making, because it's humanly not possible to train the models, but they're able to do the training model. And the solutions I talked about, the best practices I talked about, are so common sense ideas. The attention model, the beam search, or the reread model, etc. So common sense, which human beings do. So if you guys want to become NLP experts, you just have to think, okay, how do I do summarization? If I do this, okay, I'm going to write a model now. You may be inventing the next successful model too. Yeah. Yeah, you had a comment, sir? You had a comment?
Yes, I had a question. So how big are these training sets typically? Like in the case where you were talking about the force,
Mm-hmm.
do they like train it with like hundreds of millions of articles or something like that? Or are they similar? Could you like do technical papers like this, for instance?
Mm-hmm. So
Is there a theme?
right now, this research paper Richard Schwarzer has done, they have taken multiple training data sets. One data set I know for sure is two data sets called CNN data set. It's called CNN data set. The other one is called Daily Mail data set. CNN data set has around 300,000 text with summaries, and Daily Mail has almost 1.2 million news items with the summaries. They have tested that, and the summaries the model has given is very closer to what the model generates too.
Because there would be structure in those already.
Oh, yes, yes.
CNN reports in a particular way, and Daily Mail would report in a particular way, so it's not really random or arbitrary.
But at the same time, the availability of data sets is becoming difficult, because it was coincidental. The reason why CNN and Daily Mail is what CNN has this habit of, you have the big news item, but they actually summarize the whole thing in a couple of bullets. That they're taken as a data set. So you have the whole story and you have the bullets as a summary, and then that's authentic data to compare. Otherwise, if you have to create, someone asked me the question, if you have your industry, your company's information, how do you do the summaries? It's creating data sets is a big, if you guys all must have heard about how popular ML is becoming, machine learning is becoming, NLP is becoming. There's another industry which is being extremely popular, extremely making lots of money, is creating data sets. If you want, there are a few companies now making lots of money. Of course, there's a lot of outsourcing things done. If you want to create a data set, you have lots of money. Maybe you can get funding too as a startup company. Yeah.
Is it possible to create security keys so that's like encryption, decryption, like you think the summary is the key? Can you create like that?
Till now, with my limited understanding of NLP and ML, security is not the topic people are focusing on. You have the text, and model is becoming intelligent in grasping the problem statement of, if you want me to create a summary, if you want me to create a translation, I'm just doing it. But security, I don't know. I don't know the answer for the question. I don't think ML guys are really focusing on security aspect of course, that's what, if you bring it to production, of course, there's a security aspect of it. That's a different thing. But pure NLP research, ML research, I haven't seen security.
So basically, when you try to create a summary, you basically face two problems. One is the problem of compression, when you try to eliminate everything that you don't really need to convey the meaning. And the second thing that you do, you basically rank, every article presents multiple ideas. And you rank ideas by weight, and you say, this is the highest weight, this is all the way to the lowest, and you basically dissect at some point of time.
Mm-hmm.
Okay? Now, you are achieving both goals by training your model based on the CNN data set, which makes an implicit assumption that whoever created those headlines for CNN did a good job.
Mm-hmm. Mm-hmm. Yes. The model is as good as your data set. Absolutely. There's no doubt on that. If the data set is really bad, a bad quality data set, then model is also not accurate too. That's why I think the importance of data. I would say if you are doing an ML project, 80% of the time is spent on getting the right data set right. So if you don't have the data set, in this case, for example, if you have to humanly curate some data, the research is going slower there.
What about adversarial net? I mean, can you use adversarial?
Use what?
Adversarial.
Adversarial, huh?
Yeah, neural nets to avoid data sets entirely.
I don't know enough about adversarial networks to comment on that. I don't know.
Okay.
In the reinforced learning, you talked a little bit about the additional input, the global hidden state. Could you elaborate on that a little bit more, and how many statements can be combined in order to still get some sort of context out of in the hidden global state, and at what point does that get convoluted as well?
In the research the data set, the longest data story is I think 100 to 200 tokens, and the summary is I think 25 to 30 approximately is the summary that I'm coming to. That's actually a substantial progress compared to a couple of other papers where the input size was only around 75 characters, so around 10-15 words, and then trying to summarize